Hello ladies and gentlemen, welcome to another lesson. Today we're going to be talking about rational functions. We're going to review some of the stuff we've previously talked about them and then learn some more about the end behavior and some other things that we need to know about our rational functions, okay? So first of all, let's just make sure we have a formal definition. What is a rational function? So I always think of it as the form f of x equals, and then I always say h of x over g of x, where h and g of x would be polynomials, okay? Basically, what makes something a rational function is it's a polynomial divided by another polynomial, okay? And the thing that makes these functions interesting, or the things that we have to pay attention to, is the fact that they're domains. We have to actually think about them. With polynomials, we never had to do that. It always was all real numbers. But with rational functions, we have these things called discontinuities, places where our function does not exist, okay? And we have to make sure that we know how to identify those and how to look for those, and that's what we did the last couple of lessons we talked about, right? So we have two main kind of discontinuities that will come up with rational functions, and another one that we talked about but we're not really going to be too concerned with. So first of all, vertical asymptotes. Those are caused by your denominator equaling 0. Okay, if you set that denominator equal to 0, that's going to be where your vertical asymptotes are going to show up, okay? Now, the thing that makes them vertical asymptotes versus removable is that for removable, again, your denominator is going to be equal to 0, but the factor is going to cancel out with the numerator, okay? So your denominator, once again, equals 0. But in addition to that, the factor that's causing that, okay, the factor that's giving you that 0, it will cancel with the numerator, okay? So you'll see the same factor in the numerator and the denominator, okay? For example, just to kind of show you what I'm talking about, the difference there. Let's say that we had a function, and I'm going to basically already pre-factor this function, but let's say we had like x plus 1 times x minus 2, so that's a factored polynomial, and then we had that over x minus 2 times x plus 7. Okay? Well, where my denominator equals 0, that's where my discontinuities are going to occur. And at negative 7, because when I said x plus 7 equal to 0, I'm going to get negative 7. That's going to be a vertical asymptote because it makes my denominator equal 0, and it doesn't cancel with anything in the numerator. However, my x equals 2, and again, I'm getting that from setting x minus 2 equal to 0, that's going to be removable. That's going to make that little hole in our graph, okay, because it does cancel out with the numerator, okay? Those are the two big ones that we have to pay attention to with rational functions, okay? There is another kind of discontinuity that we talked about, which is a jump discontinuity. That's caused by piecewise functions. We're not really going to be delving too much into those in this chapter. We're mainly focused on the rational functions, so your main goal is to focus on these first two. Make sure you know how to find those and the difference between those, okay? All right? Now, that's what we talked about before. Let's add on kind of a new wrinkle, okay? This time we're going to talk about what a horizontal asymptote is. So, vertical asymptote is a discontinuity caused by where your denominator equals 0. A horizontal asymptote is actually end behavior. Okay, a horizontal asymptote is a kind of end behavior, okay? You can think of it as being very similar to a vertical asymptote in that as your function goes out towards infinity, okay, so as your function, we'll call it f of x, goes out towards infinity, okay, it'll start to follow, I'll put that in quotes, the horizontal asymptote. And again, it's going to act like other asymptotes where it's going to get closer and closer and closer to that value without actually ever reaching it. So, for example, let's say I had a function, so here's my xy axis. Let's say I had a function that looked like this, right? And let's say that, I don't know, 3 is the value here. We could say that this is a horizontal asymptote because as our function goes out, it's going to get closer and closer and closer to that value but never actually reach it, okay? And again, we think of this as an end behavior because it's something our function is going to do as it goes out towards infinity and as it goes out towards negative infinity, okay? Very similar to with polynomials, we had end behaviors that was either up or down basically as it went out. With rational functions, we now kind of have this new wrinkle where, yeah, it can go up, it can go down. It also can kind of follow a horizontal line and get closer to that as it goes out and start to kind of look like that as it keeps going, okay? Again, just like the vertical asymptote, it'll get closer and closer and closer, but never actually reach that value, all right? So I actually have a picture here. So if I, let's clear the slide, you can kind of see that picture a little bit better, okay? But you can see this function as it goes out towards infinity, as it goes out towards negative infinity, it is following this horizontal asymptote. It's getting closer and closer and closer to that value without actually ever reaching it. Okay. Now, in terms of some exploration I want you guys to do, I want you to go ahead, I want you to take these three functions, and I want you to graph them in Desmos, okay? And I want you to try to figure out what the horizontal asymptote of each of them is. What is it approaching as it goes out towards forever in your x in either direction, okay? And then see if you can come up with a pattern. We'll talk about it in a second, but see if you can come up with a pattern about why it's doing certain things, okay? Go ahead, pause the video, try that, and then we'll meet back and talk about what you found. All right, so hopefully you went through and you tried to find those horizontal asymptotes. For the first one, you should have seen the equation y equals 0, the horizontal line y equals 0. That's what it approached as it went out towards forever. For the second one, as it went out towards forever, it approached the line y equals 2, horizontal line at 2. And then the last one did not have a horizontal asymptote. However, I said a big but right there, okay? We're actually going to see that it's going to have something called a slant asymptote we'll talk about in a moment, where it actually follows a diagonal line as it goes out. And we'll talk about why that occurs in a second. But before we do that, let's go ahead and let's kind of formalize these rules we have here for horizontal asymptotes, okay? There's three main things that can happen, okay? And I say n and m here. What I'm talking about is the degree of the numerator and the degree of the denominator. So if we think of our rational function, okay, and we think of the numerator as being x to the n, and then whatever else is up there, right? And then we think of the denominator as x to the m, and then whatever else is down there. These would be the highest degrees, okay? So the degree of the numerator and the degree of the denominator, okay? There's three different things that can occur. Either the degree of your numerator will be less than the degree of your denominator, okay? So something like, let's say, x squared over x to the fourth. And again, who knows what else is part of this. But if you have something like this, then you're going to have a horizontal asymptote at y equals 0. Okay? So your horizontal asymptote will be at y equals 0. Okay? If they are equal, okay, if they're equal, so something like, let's say, x to the third over x to the third. Okay? And then who knows what else is there. All right? For those, we're going to look at the leading coefficients, so the numbers that are multiplied by those things of the highest degree. I'll call those A and B. Your horizontal asymptote is going to be y equals A over B. Okay, that's going to be your horizontal asymptote. Okay? And then if n is greater than m, there is no horizontal asymptote, although we're going to add a little something onto that in a second. Okay? So three things can occur. You either have a horizontal asymptote at y equals 0 if the degree of the numerator is less than the denominator. At a over b, the ratio of the leading coefficients, if they're the same. And then if the numerator is larger, there is no horizontal asymptote. That follows along with our last slide we just did, right? This one, the numerator, the degree was smaller than the denominator, and we got y equals 0. Here the degrees were the same, 4 over 2, that equals 2. That's going to be our horizontal asymptote. And then the last one here, this one does not have a horizontal asymptote, okay? But we're going to see in a second, actually, it's this thing called a slant asymptote. And that is going to occur if the degree of the top function is exactly 1 greater than a bottom function, okay? It has to be only 1 greater. And the way that you're going to find what that slant asymptote is, basically it's a diagonal line that it'll follow as it goes out. You're going to find that by dividing, okay? If you divide the numerator by the denominator, what you get left over is actually the slant asymptote. What is this function going to follow as it goes out towards infinity? It's going to follow this diagonal line, and you can figure out the equation of that as you go, okay? So for example, if I had this function here, what you want to first notice, we're going to see later when we kind of do all these problems together and start to do sketches of these, one of the things is going to be find the m behavior, right? And so what I'm going to do is I'm going to look at it and say, oh, the degree of my numerator is 1 greater than my denominator. I know, therefore, I have a slant asymptote. Then I'm going to say to myself, okay, how do I find that? I'm going to do that by division, and I'll set up my division problem. So in this case, we're doing x squared minus x, and we'll add on that placeholder for the constant term, and we're dividing in x plus 1. And then whatever I get out is going to be my slant asymptote. So x goes in x squared x times. We're going to get x squared, and we're going to get plus x. We're going to subtract, cancel. We are subtracting this as well. We're going to get negative 2x plus 0. X is going to that minus 2 times. Okay, and we could keep going and do all that, but we actually don't need to. The remainder doesn't matter, just this portion right here. So x minus 2, that's what my function is going to basically converge around. It's going to get closer to that as I go out towards forever, okay? And we'll talk about later how to graphically show that. But for right now, just recognize that, okay, if you were to graph this in Desmos and look at how it goes out towards forever, if you put x minus 2 in there, you're going to see it's going to follow that as it goes on and out forever, okay? All right, so this is going to be your homework. I'll also have this posted later where you're supposed to submit it, so you can see it down there as well. But I have basically 3 problems for you, okay? 3 different functions, and I want you to find the 4 following things, okay? Number 1, I want you to find any discontinuities that this function has, okay? That means any vertical asymptotes or removable discontinuities. To do that, just as a reminder, you're going to set your denominator, I'll call that d, equal to 0. Okay, set your denominator equal to 0, solve, whatever you find, those are your discontinuities. If it cancels out with the numerator, it's removable. If it doesn't, it's a vertical asymptote. The next thing you're going to find is the roots. Now, we haven't necessarily talked about how to do that with rational functions, but you actually already know how to do that from the last chapter. You just set the numerator equal to 0. Okay, so set that numerator equal to 0 and solve and see what you find. That'll be your roots of this function, okay? Then the last things that we talked about, the horizontal and slant asymptotes. So remember, you're going to look at your degree of your numerator and the degree of your denominator, and based off that, that's going to tell you what kind of end behavior you have, whether it's a horizontal asymptote or a slant asymptote, or neither. It could be neither of those things if the numerator is greater and it's not 1 greater, it's more than 1 greater, okay? So those are the 4 things I want you to do for these 3 problems. Find the discontinuities, the roots, and then really these last 2 are kind of one thing. Find the end behavior. Does it have a horizontal asymptote, slant asymptote? Neither. Okay? Thank you all for watching.